Hello everyone, this is Professor Mahesh Pardeshi from Parvatibai Genba Mose College of Engineering, Wavodi, Pune. In the today's lecture, we will discuss about the different types of fluid and their classification. Here you can see that the types of fluids are ideal fluid, real fluid, Newtonian fluid, non-Newtonian fluid, and ideal plastic fluid. These are the different types of the fluids we have to study. Means we have to just see the basic definition of this fluid. Okay. You can see in this diagram, these different types of fluid are shown, and the graph is shear stress to the velocity gradient. Shear stress versus the velocity gradient. Okay. You might be very clear about this shear stress and velocity gradient. In the expression of the dynamic viscosity, we will study this part. That is tau is equal to mu into du by dy. Tau is equal to mu into du by dy. Okay. In that expression, we will discuss all about this shear stress and velocity gradient. Now see one by one the definitions of this fluid. Actually see this ideal fluid means what? The fluid which is having no viscosity and no shear stress. Ideal fluid means what? The fluid having no viscosity and no shear stress. But this is not practically happen. Every fluid has some specific, every fluid has some shear stress and every fluid has some viscosity. Okay, and that fluid is called as real fluids. In real, this is happens. Means viscosity is there and shear force is there. Okay, now see one by one. First is the ideal fluid. A fluid which is incompressible and is having no viscosity is known as ideal fluid. Ideal fluid is only an imaginary fluid as all the fluids which exist have some viscosity. See, in case of the ideal fluid, these fluids have no viscosity and no shear stress. Okay, but in reality, every fluid must have some viscosity. Every fluid has some viscosity. That's why these fluids, ideal fluids, are imaginary fluids. These ideal fluids are the imaginary fluids. Now, second is the real fluid. A fluid which possesses viscosity is known as real fluids. Fluid which possesses viscosity is known as real fluids. All the fluids in actual are the real fluids because every fluid having some viscosity in fact is actual. That's why actual fluids are called as the real fluids. Okay. Now next is the Newtonian fluid. See, you can understand very simply which fluids obeys the Newton's law of viscosity. That fluids are called as Newtonian fluid. Okay. See the Newtonian fluids, a real fluid in which shear stress is directly proportional to the rate of shear strain is known as Newtonian fluid. And what is this? Shear stress is directly proportional to rate of shear strain. It is the Newton's law of viscosity. Okay, that's why the fluids which obeys the Newton's law of viscosity, these fluids are called as Newtonian fluids. Okay, now next, non-Newtonian fluids. Non-Newtonian fluids. Okay, real fluids in which shear stress is not proportional to the rate of shear strain or the velocity gradient is known as non-Newtonian fluids. Okay, in case of the non-Newtonian fluid, shear stress is not directly proportional to the rate of shear strain. That fluids are called as non-Newtonian fluids. Understand? Now last is the ideal plastic fluid. Ideal plastic fluid. A fluid in which shear stress is more than the yield value. Shear stress is more than the yield value. You can see here this point. This point. Shear stress is more than its yield value. Okay. And shear stress is proportional to the rate of shear strain. or the velocity gradient is known as ideal plastic fluid. Ideal plastic fluid. Okay, the curve for the ideal plastic fluid is starts from this value initially the shear stress is not zero. See, for every other cases, that is ideal Newtonian non-Newtonian fluids, the shear stress at the beginning is zero. At the starting point, shear stress is also zero and velocity gradient is also zero. But in case of this ideal plastic fluids, at the initial point, there is some value of shear force, shear stress. There is some value of shear stress. Shear stress is not zero. It is having some value and the graph is starting from this point. Okay, this is called as ideal plastic fluids. Okay, these are the different types of fluids. Okay, now we will see the classification of fluid. Next point is the classification of fluids. There are wide variety of fluid. There are wide variety of fluids flow problems incurred in practice, and it is usually convenient to classify them on the basis of some common characteristic to make it feasible to study them in a group. See, in actual, there are large number of problems which are incurred in the practice means while application. In these fluids, there are large number of problems occurred. So, in order to solve that problem, it is necessary to group that fluids, okay, in a various groups so that we can easily identify every fluids and every problems. Okay. Now, see the first is the viscous versus inviscid region of flow. Now see the basic part, what is meant by viscous. We already see the part that is viscosity. What is meant by viscosity? Viscosity is nothing but the resistance to the flow of one layer to the another layer. Okay, while moving the fluid layers apply the resistance on each other. Okay, this is called as viscosity. Okay, now here what is meant by viscous flow? The flow in which there is an internal resistance, there is an internal resistance between the two layers. Okay, you just simply remind that the viscous flow means what? The flow which applies internal resistance in between the layers, that flow is called as viscous flow. What is meant by this inviscid region of flow? It means there is no internal resistance of flow and the flow is smoothly going on. Okay, that that region of flow is called as inviscid region of flow. Okay, see here, when two fluid layers move relative to each other, a friction force develops between them and the slower layer tries to slow down the faster layer. See carefully. When the two fluid layers move relative to each other, a friction force develops between them. Friction is develops between them because the velocity of one layer is less and velocity of other layer is more. That's why if there is a difference between these velocities, due to that difference there must be friction. There must be friction. Okay, and slower layer tries to slows down the faster layer. Slow layer will try to slow down the faster layer. Okay, this internal resistance to the flow is quantified by the fluid property viscosity. Means this internal resistance is nothing but the viscosity of the fluid. Okay, which is a measure of internal stiffness of the fluid. Which is the measure of internal stiffness means binding property of the fluid. Okay, viscosity is caused by the cohesive forces between the molecules in the liquids and by molecular collisions in case of gases. Okay, viscosity is caused by the cohesive forces in case of liquids and molecular collisions in case of gases. Okay, next point. There is no fluid with zero viscosity, and thus all the fluids flows involves viscous effect to some degree. Some degree means some less degree. At least some degree of viscous effects are there in every fluid. In every fluid. Okay, flow in which the frictional effects are significant are called as viscous flows. Frictional effects means internal resistance. Flow in which the internal resistance are significant, that flows are called as viscous flows. Okay. However, in many flows of practical interest, there are regions, typically regions not close to the solid surface. This is very important line, not close to the solid surface. I will explain with the next figure, where the viscous forces are negligible, small, compared to the inertial or pressure forces. Compared to the inertial means other forces, compared to other forces. Okay, neglecting the viscous term in such inviscid flow regions greatly simplifies the analysis without much loss in the accuracy. I will explain with the this next figure. You see the figure carefully. Okay, this is the streamline flow. Okay, now the flow is streamline. Okay, here. Okay, due to any body which is present in the fluid, due to that body the fluid is moving in this direction. Okay, at this surface point. Okay, at this surface point the velocity of the flow is zero. At this point the velocity of zero, and this region between these two lines, the region between these two lines is called as viscous region. Okay, this region between these two lines is called as viscous region. Here the viscous forces are very heavy because these forces are near to surface. Near to surface, what happens, there is a large amount of internal resistance because this is a solid surface. Because of this solid surface, there is a large internal resistance between the solid surface and the liquid surface. Means at this surface point there is a large amount of internal resistance, large amount of the viscous force. Okay, as we move towards this point above or below or anything, as we move away from this point, the viscous effects are lowers down. As we move from this boundary point away from that boundary, the viscous effects are lowers down. Okay, and here the viscous effects are very less. At this region the viscous effects are very low. That's why this region is called as inviscid region. And this region is called as inviscid region, and here the flow is inviscid external flow, and here you can see that inviscid internal core. Why this is called an internal core? Because it is, this is in between these two boundaries. In between these two boundaries means there is a large amount of the viscosity is there in between these 2 points. Okay, here you can see that fully viscous flow. The flow is fully viscous, means the viscosity is very high at this point. Okay, and here is also inviscid external force because here is the viscosity is very less. At this point viscosity is very less. Okay, understand? Okay, now see the next point, classification of fluids. Classification of fluid flows. First, internal versus external flow. Here you can see that internal versus external. So see the point. The fluid flow is classified as being internal or external depending on whether the fluid is forced to the flow in a confined channel or over the surface. See the next line. The flow of an abundant fluid over the surface, such as plate and weir, is called as external flow, not the pipe flow. Here by mistake it is given. Flow over the plate, flow over the weir, flow over the channel is called as external flow. Is called as external flow. See the next line. The flow in the pipe or duct or conduit is called as internal flow if the fluid is completely bounded by the solid surface. Here the point is important, completely bounded by the solid surface. The pipe or duct, it is closed in the surroundings, all the points are closed. Okay, the completely bounded by the solid surfaces, that's why the pipe flow is called as the internal flow. But in case of the weirs, in case of the plate, in case of the channel, The top portion is subjected to atmosphere. That's why this flow is called as external flow. That's why this flow is called as external flow. Okay. Water flow in a pipe, for example, is the internal flow, and the airflow over the ball or over the exposed pipe during a windy day is the external flow. Okay, means subjected to atmosphere. Okay, understand this point, internal versus external flow. Next point, compressible versus incompressible flow. Here the flow is classified as being compressible or incompressible depending on the level of variation of density during the flow. See here, if there is a change in the density, if the density of the fluid is increases, that means that fluid is a compressible one. Okay, and if the density remains constant, means the fluid is incompressible. Okay, this is basic. Now see, incompressibility is an approximation, not correct one. Okay, and a flow is said to be incompressible if the density remains nearly constant throughout. Means the density is constant, that fluid is called as incompressible. Okay, means this fluid cannot be compressed. This fluid cannot be compressed. Okay, means there is no change in the density of that fluid. That fluid is called as incompressible fluid. Therefore, the volume of every portion of the fluid remains unchanged over the course of its rotation, its motion when the flow is incompressible. Next line, the densities of the liquid are essentially constant, and thus the flow of the liquid is typically incompressible. Generally, the flow is incompressible. Okay, therefore, liquids are usually referred to as incompressible substances. See, in case of the gases, there is a large amount of compressibility in case of gases. You see the large amount of the compressibility in case of gases, but in case of the liquids, this is not happens. In case of the liquids cannot get compressed. That's why it is treated as a incompressible. Okay. See the next point. A pressure of 210 atmosphere, for example, cause the density of the liquid water at 1 atmosphere to change by just 1%. Means when we apply the pressure of 210 atmosphere, when we apply the pressure of 210 atmosphere, the change in the density of the water is just 1%. Is just 1%. Okay, now see the next point. Gases, on the other hand, are highly compressible means even if there is a small amount of change in the pressure, there is a large amount of change in the density. Okay, here you can see that a pressure change of just 0.01 atmosphere, for example, cause a change of 1% in the density of atmospheric air. Here you can see that the difference. Here in case of the gases, we change the pressure by 0.01 atmosphere, and for liquids, water, we have to change the pressure for 210 atmosphere for the change of 1%. For the change of 1%, here you can see that 210 atmosphere and here 0.01 atmosphere, very negligible, very small change in the gases, very small change in the pressure of the gases can create a large amount of change in the density. Okay, that's why the gases are highly compressible. Here you can see that the gases are the highly compressible. Gas flows can often be approximated as incompressible if the density changes are under about 5%. If the change is about less than 5%, then we can treat as incompressible gases. Okay. The compressibility effects of an air can be neglected at the speed under about 100 meter per second. If the speed is less than 100, we can neglect the compressibility effect. Okay. Next is Laminar versus turbulent flow. Laminar versus turbulent flow. Some flows are smooth and orderly while others are rather chaotic. The highly ordered fluid motions characterized by smooth layers of the fluid is called as laminar. Here you have to take care of this word, that is smooth layers. That is smooth layer. Here you can see in this diagram laminar. Here the layers are flowing very smoothly. There is no turbulence between the two layers. Every layer is moved very smoothly. That's why this flow is called as laminar flow. Here in diagram you can see these three diagrams. First one is the laminar. Here the flow is very smooth. Every layer is flowing smoothly. That's why this layer is called as laminar. The flow is called as laminar. Okay. The flow of high viscosity fluids such as oil at the low velocities is typically laminar. This is the example. Okay. The highly disturbed fluid motions that typically occurs at high velocities and it is characterized by the velocity fluctuation is called as turbulent flow. In the last diagram you can see here in the third diagram, highly disturbed fluid flows. The flow is highly disturbed. See this portion. The flow is highly disturbed. Every layer is mixed into each other. Okay, and there is a large number of velocity change. Here the velocity fluctuation is more. Okay, this flow is called as turbulent flow. This flow is called as turbulent flow. Next is the flow of the low viscosity fluids such as air at the high velocity is typically turbulent, because high velocity, due to that high velocity there is a more amount of collision between the different particles of air. Air contains different particles, and due to that high velocity that particles are collides with each other, and that's why this flow is called as turbulent flow. Okay, now the flow that alternates between laminar and turbulent is called as transitional flow. In this diagram you can see that here that portion is laminar and here the portion is turbulent. So this middle portion is called as transition of flow or transitional flow, where the flow is going from laminar to turbulent or turbulent to laminar, both way. Okay, that flow is called as transitional flow. Okay, understand this point? Now next is the natural, that is unforced versus the forced flow. Okay. A fluid flow is said to be a natural or forced depending upon how the fluid motion is initiated. How the fluid motion is initiated means started. How the motion is started. Okay. In forced flow, the fluid is forced to the flow over the surface or in a pipe by external means. By external means is the important word. By external means such as pump or a fan. When the flow is created due to the external means, that is pump, in that case we can say that the flow is forced flow. The flow is forced flow. Okay, in this next part, that is natural flows, any fluid motion is due to the natural means such as buoyancy effect, which manifests itself as the fluid rise of the warmer fluid and the fall of the cooler fluid. Here you can say that in case of the natural fluid, there is no external agency, there is no external means to start the flow. There is no external means to start the flow. The fluid is flowing naturally. The fluid is flowing naturally. Here first line you can see that the fluid motion is due to natural means. There is no external means. Okay. Huh. In solar hot water system, for example, the thermosymphonic effect is commonly used to replace the pumps by placing the water tank sufficiently above the solar collectors. This is the example of this natural and forced flow. And last point is the steady versus the unsteady flow. Steady versus the unsteady flow. The term steady and uniform are used frequently in the engineering. Frequently we can use this term, that is steady and uniform, and thus it is important to have a clear understanding of their meanings. Okay, the term steady implies that there is no change at a point with time. Here with time is a very important part. With time, no change at a point with time is nothing but the steady flow. With respect to time is nothing but the steady flow. Opposite of the steady is called as the unsteady flow. Means there is change in the various properties of the fluid with respect to time. Okay, and the term uniform implies that no change with location. Means there is a no change in any properties of the fluid with respect to location. That is called as uniform flow. That is called as uniform flow. Okay, and if there is a change in the properties of the fluid with respect to location, and that flow is called as a non-uniform flow. That flow is called as non-uniform flow. All of you get the idea of this? Okay, thank you.